All right, so today we're gonna continue our conversation of quantum field theory by talking about path integrals for free scalar fields. So we spent quite a bit of time talking about path integrals in quantum mechanics. I wanted to highlight a set of things that happen. I wanted you guys to have an intuitive way of thinking about propagators. So what is propagator? There are various ways to say it. The propagator is a matrix elements of evolution operators. That's one way of saying it. Another way of saying it is that it's Green's function for Schrodinger operator. Right, that's another way of saying it. And then when you Fourier transform in space and time, what it is, it's just the inverse of the equation of motion. Well, equation of motion, as in like the Schrodinger operator, the inverse of that, right? And then there was this I epsilon prescription that we talked. It's going to come. I'm going to go over it again and repeat the I epsilon prescription. Hopefully, I think you need to see it a couple of times. I'll make a comment about causality. All right, summary of lecture 19. We actually, towards the end, we started developing a perturbation theory for small interactions. The thing that we pointed out, so you take your flat free Lagrangian, you add to G some small coupling V potential, right? It's not that G has to be small. What has to be small is the contribution of this term to the action that has to be small compared to the contribution of the free part of the action, right? So that is the dimensionless parameter we're talking about. That's the perturbation theory. All right. In the first order perturbation, so here's what the propagator is. So of course, in this perturbation theory, there will be a free part, free propagator K0 that we calculated. There will be a first order in the contribution of the interaction. So we calculate the propagator, the free propagator, using the path integral explicitly, and this is what we found before doing any Fourier transform. So it's 1 over, what you need to see in this is that it's 1 over t to the power of d minus 2. This is a retarded propagator, right? It better be evolving only forward and not backwards in time. And then there was e to the power of I m something over t, right? The distance over t. This is the Gaussian phase. This 1 over t to some power tells you what? Tells you that if this is a particle and these 2 points are, if delta t, tf minus ti is arbitrarily small, this is very, very small, there is a non-zero amplitude for the particle to appear arbitrarily far away. There is no sense of a light. There shouldn't be. This is a non-relativistic particle, right? But then the important point that we started talking, we said this in lecture 2 or 3 back then, was that, well, this is a quantum mechanical result. You might be tempted to say, if you replace the dispersion or the expression for energy, so this result that we just found comes from E is p squared over 2m, right? Plus v of, well, there's no potential for now. It's tempting to say, oh, if you just take a relativistic expression, p squared plus m, maybe you'll see causality. Maybe you'll see a light cone, sharp light cone. Before saying that, let me just, we'll get there. But what we did was that we took this expression, we Fourier transformed this, right, in space and time. What we got out of it was momentum conservation, energy conservation. These have to do with the symmetries, translation in space and time. And then you get IH bar over EF minus PF squared over 2M, right? This is basically the Schrodinger operator in Fourier space, right? And that's the meaning of saying that, that's exactly what it means to say that the Green's function is the the propagator is the Green's function for the Schrodinger operator, right? So these Dirac delta, I said that. All right. Then we said that for a Fourier transform in time to energy, for it to converge, we had to do this I epsilon thing, this I epsilon prescription, right? And then it gave us a single pole, right? The single pole comes from this. All right. Now let's pick a relativistic dispersion. Everything goes through. After Fourier transform, you get conservation of energy, momentum conservation of energy. This structure of it will be IH bar over E minus square root P squared over 2M. Oh, sorry. There's no 2M. P squared plus M squared. Setting speed of light equal to 1. Right? And then you'll have to add the I epsilon for the Fourier transform convergence. This still suffers from the same feature. Even though you plugged in the relativistic dispersion, it still shows this property. This was the calculation that we started in lecture 2 with. We said that if you calculate the propagator with a relativistic dispersion for a single particle, there will be an amplitude for it to instantaneously be really far away. And you could calculate that amplitude. It's if this distance, this distance is very much larger than time, it basically falls off as e to minus m square root x squared minus c squared. So there is a non-zero, exponential small, but non-zero violation of causality. That's bad. That's awful. And how does relativity fix it? Well, relativity tells you that this is not your dispersion. Well, this is your dispersion, but Schrodinger operator is not the equation you should be dealing with. You should be dealing with the Klein-Gordon operator. When you take the Klein-Gordon operator into account, what you obtain is, I think I have it right. Well, okay. Let me write it here. Maybe I have it on future slides as well. We did this before, right? You end up with E squared minus K squared plus M squared. Instead of what is this expression? Instead of this expression, you land on this expression. And if you do I epsilon, you need the I epsilon for it to converge, right? You notice that now you have two poles, right? As opposed to this. Every pole is a particle. This one only had a particle. The other pole corresponds to the anti-particle. And I said back then, I just promised, I don't think I did a calculation. I just promised that once you do this relativistically, the anti-particle is contribution will come out exactly the right amount with negative sign to cancel the propagator outside the light cone. So you get a sharp light cone, right? Causality, you could use say all these words, causality, relativity, all these are like infinitely tied, right? Will tell you that the single particle quantum mechanics is inconsistent. You must have antiparticles, right? Which already puts you in this world of like number of particles is not conserved, blah, blah, blah. All right. So it's just like a throwback to a Thursday many weeks ago. All right. Very good. I also, and when you do Fourier transform in space and time, basically what all you're doing is that this is your Schrodinger operator equation, the Schrodinger operator Green function after Fourier transform is just this equation. So you're literally inverting the Schrodinger operator in the momentum space, energy and momentum space. So that's everything that we needed to know about the K0. Are there any questions about K0? By the way, recall that when we did this, when we did K squared, well, I think let me just write it this way: omega squared. I forget what the sign was. Right? When we did this was Feynman prescription, right? You go under one pole and above the other, right? So there was another prescription that would correspond to retarded, advanced, right? But if what happens if you go above below both? That's a commutator. Use a commutator, right? This is time ordered. This is fine, time ordered. All right, very good.
How do you decide how to choose whether we use the timer or
what do you want to calculate? Do you want to calculate time or the correlator? You want to calculate the commutator? Right? This, like what? This is the structure of the two-point function and the complex K0 plane, right? What you want to compute is like how you what is your I epsilon prescription is about what you want to calculate, right? So the reason that we had in the commutator we had two terms was we're subtracting the two, so we deformed and went on. Good. All right. Next, we talked about very briefly perturbation structure of it. So K1 looks like this. And basically the way to think about it in this picture is that schematically, it looks like this is the way to think about it, that interaction happens sometime between TF and TI at some point. There's a V term, right? So what do you, if it happens at Q prime T prime, you first write the propagator from here to T prime. You insert your V, then you write another propagator. So it looks like V propagator. But then if you look at the first order perturbation, you're integrating around this everywhere in between, right? This is all cartoon, right? Like this is the structure of perturbation. Those cartoons represent this integral structure. It's not to be taken literally. The interaction not happening at a point in space time, right?
Just to make sure.
Yeah.
So when I'm doing integral of d3 dt, so I'm integrating all of these points in between the two initial and the final points, right?
Yeah. Because remember that when the interaction contributes to the action, which includes an integral over space and time, right? The structure of perturbation theory at higher level now could be written elegantly. You have a whole bunch of these V's and you're inserting them, integrating this way. But something you notice is that there will be time ordering coming into play. But okay, so we'll come back to that. All right. Do you know what I mean by that? If you do the path integral with an operating insertion here and another operating insertion here, right? I just say T1 and T2. If I do the path integral with T1 and T2, that automatically time orders. The path integral automatically time orders. Right? We said that before.
So when you integrate it, will it not swap the two, or?
When you integrate it, T2 and T1 are variables. If you pick T2, so you get an answer, right? You get an answer. The answer is such that if T2 is larger than T1, that corresponds to the operator calculation correlation function or QI. It corresponds to this QI, QF, TF, V of Q prime T2, V of Q prime T1. Right? If you did the same integral and T1, the integral doesn't care about with it, right? If you do the integral with T2 less than T1, it's the opposite order. Do the integral. It's the only way to. I think I'll try to put it as a. So I skipped scattering matrices last time because we're going to spend a lot of time talking about it. But I changed my mind. I'm going to very, very briefly talk about scattering matrices. So we're going to spend a little bit more time on this quantum mechanics example because I think it's important to hear this and hear it again and hear it again. All right. This is an expression this is a statement you might hear from a lot of physicists. What are the observables of quantum field theory in flat space? Some people say there are scattering matrices. Scattering matrices are definitely part of the observable. Some people might say correlation functions. We're going to spend a lot of time relating the two. Right? But at the level of this quantum mechanical setup, I want to define them, relate them very quickly. All right? So I claim that path integral formulation of quantum mechanics is an alternative formulation. And for that, I said, well, the path integral calculus for us, the propagator, now you have a name for this. What else does it calculate? It calculates for you matrix elements of arbitrary operators. That's good. Can you use the path integral to calculate the S matrix? Can you use the path integral to calculate correlation functions? Those are the two things we're going to talk about. We're going to do it at the level of the quantum mechanical case because it's easier. Good. If we're claiming that this is a reformulation of quantum mechanics, I should be able to do all of that. And the relation between them become clear. So what is S matrix? What's a scattering problem? Scattering problem is the following. Think of first ordinary quantum mechanics before doing path integration, right? So what is a scattering problem? Scattering problem is that you have some potential like this. Crucially, potential dies away at infinity really, really fast, right? Why? Then if it dies away really, really fast, if you're all the way down here, right, your particle doesn't feel the potential. So the solution to Schrodinger equation here are plane waves. This is far away left. Then it comes all the way, right? It hits this. Part of it is reflected. Some stuff happens here, right? Part of it is reflected and far away again. It looks like plane wave. Part of it goes through and far away. It looks like plane. In the middle is some sort of wacky thing that you've learned, like how to calculate. Right? You've learned a lot. But these are asymptotic states. To make sense of that, the potential has to die away fast, right? S matrix is a similar thing, except that you say the potential. Now, let's say we're doing quantum mechanics in quantum field theory in 0 + 1 dimensions, right? It's the same thing. You say my potential, my interaction potential, far away at long time ago, in time, near minus infinity time was turned off. Late time is turned off as well, right? So interaction was somebody turned on the interaction long time ago, then let it evolve, and then slowly to dial it down. These are a set of words that we're saying in physics. This is not how you mathematically make sense of it. Right? Mathematically making sense of this, I don't know if we're going to have time to go through this. It's a beautiful formulation, and the only book I know that does this properly is one. But I have so much to say about that. It's a beautiful story. But the bedtime story physicists tell themselves is that when you turn on the interaction at some point, long time ago in the past, and turn it off long time later in the future. This makes no sense. Hopefully that's pretty clear, right? When you write down the action, you've written down the action has an integral from minus infinity in time, the contribution of that interaction, until plus infinity in time. So you're sort of like modifying that interaction, late time and early time. That's a cartoon picture. It's not quite cartoon because it could be made rigorous, but the right side of words. All right, but that's what you want to think about. So we say we adiabatically turn off the interaction. Adiabatically so that the wave functions evolve slowly, or you could have the WKB. Right? So this is sensible. These pictures are WKB kind of pictures, right? Now, what is the S matrix? S matrix is the overlap of incoming and outgoing particles. It's the overlap of this wave function and what comes out, which is those two. If you add the time to this picture, right? Now you see what happens. So this comes in, if you added time to this picture, you could view it this way. Something came, right? There was some potential here. It scattered it off like this. Went through it or scattered it off. Now you could think of this potential as another particle, just a very, very heavy one, right? So this was a collision in a sense. This looks like a collision of 2 to 3 collision. So this was a particle that sits around, where it is, roughly speaking. But the big picture we're going to be working with as scattering is something like this. A bunch of particles come in, they interact, a bunch of particles go out, right? In space-time, this is in the same, it's a cartoon, the same way that this is a cartoon. The interaction doesn't happen in a particular time or a particular place in space-time. To calculate the interaction, S matrix, you have to integrate over this cartoon thing over any point in space-time. So in perturbation theory, that's what the structure that comes out, right? So these pictures are the same cartoons as these level of thin cartoons. What you're dealing with is integrals, right? These are Feynman diagrams for those integrals. These are Feynman diagrams are diagrammatic way of, it's economic way of writing some ugly integrals. All right, so what is S matrix? It's the overlap of incoming and outgoing. These are plane waves. They're solutions of free Schrodinger equation. If you want to think of the canonical quantization, the free particle out is, there's A out, A dagger out, and then free particle in is A in and A dagger in. So you take some psi initial in. That's saying that instead of a wave packet, instead of a plane wave, take an initial wave packet. This is just free field theory, right? Free quantum mechanics, free particle. Bring it in, that's your initial thing. And then the out will also be another set of wave packets, right? Like view it as, we're talking about the multi-particle theory. So a wave function comes in, a wave function goes out. And you have to take the limit of Ti going to minus infinity and Tf going to minus infinity. This is what the S matrix is. When people say S matrix is unitary, what do they mean? It means that this is a unitary operator. There are lots and lots of subtleties regarding the S matrix. At the level of this course, we just leave it. We'll see how much time we'll have towards the end of the semester. I would like to actually discuss more about the subtleties of S matrix later on. But for now, this is what you need to know. All right? Any questions? So let me just put some equations to these, this cartoon picture. So we're doing single particle quantum mechanics. In the first order in Born approximation, you bring in some psi in, right? So there's psi initial in comes out. You evolve it by e to the power of I h tf minus ti, right? What is this? This is the state at some later time. This is evolved by propagator. Right? It's just evolved. This is being evolved by propagator, right? So this is a state at some later time. Q of f, T of f. Q of f, right? So what have I done? I've just stuck in QI, TI, QI, TI. This is a long time ago. This is the propagator. I'm integrating over this. Right? Only QI. I'm integrating over only on QI because TI is just some initial time. Then I'll have some psi out that I have to take the star out because I'm calculating an overlap. And then S matrix is as we said, it's an integral over dqf of this beast. Right? if you expand it, you're gonna see that actually. Do I wanna? Oh, let me do this on the board. I think I want to do this properly. Yeah. All right. So you start with some psi initial n that you're going to expand and at some time t prime in this basis. This is a resolution of identity. Then you evolve it by e2 minus ih tf minus ti, and then look at the overlap of it with some psi final out, right? Here I'm going to insert some q double prime. Oh, sorry. Ti. It should be ti. Tf or qf. This is qi. Qi. I'm integrating over dqi. Okay. Now that I inserted those, and so on. E to minus. So it will be qf. I'm using Schrodinger notation, so this I shouldn't put this. I should not. That's clear. Ui dqf, right? So what is this? This is the propagator k naught, and this is the initial wave packet. That's the final wave packet star, right? And what are you integrating over? You're integrating over all the propagate. So yeah, well, you're integrating over all the possibilities of going from Ti to Ts, right? From here to here, from here to here. But all right, what was the free propagator? The free propagator, what it contained was essentially energy momentum conservation. That was basically the physics of free propagator, right? So the free propagator is boring. The part of it that the contribution of the free the part is going to be super boring. So we just put it here. What it tells you is that the particles that came in, the waves continue forever, right? So you could just, yeah, that's what happens. There's an energy and there's a clock that just goes around with that energy, and then there will be an overlap. There will be just like as is the case in visual quantum mechanics. It's like a double slit experiment, but you're doing path integral everywhere. It becomes more interesting when you take the first order perturbation into account. So there will be K0. So this is the S matrix, right? There's a piece of the S matrix coming from K0. We're going to call that S naught. Then there's a piece that's coming from K1, right? And this is what it looks like. As I'd argued, well, actually, is this the, yeah, as I'd argued, what it looks like is that this K naught looks like K0, VK0. There's an integral over it. So this piece is like this picture. There's an integral over where the interaction happens. So this is a perturbation theory for the S matrix and Feynman diagrams. These diagrams, organize them for you. I think that is all I wanted to say. Yeah, let me not say this. All right. Any questions? Yes. Well, your Hamiltonian has this propagator wrote as a path integral. And the path integral, there was S0 plus S interaction, right? We expanded that to the first order. Zeroth order this.
Here we are going to be indicating about the spatial time slices which we are inserting in between, right?
The QI and QF, yeah. Early physics. So these intervals, these intervals are sort of trivial. It's sort of saying that you took your side initial. Let's say your initial eigen. It's just this included a sum over a bunch of momentum nodes. This sum is that sum, and your late side out is similarly, right? The sum over a bunch of momentum nodes. If I focus on a single node, as we usually do, right? These integrals go away because you only care about the carry.
I'm just trying to see like here we also have an integral over that time slices in the middle also, right? When I was drawing K1. So it was
All right. Which term are you talking about?
the one which you just mentioned.
K1. So K1 has the following structure that this is Ti, this is Tf. K1 has the structure of it's an integral over d of q prime t prime of a term which looks like propagator v propagator. That's the structure. But yeah, that's what it is. As a path integral, it's also the same, right? This it's an integral over this path.
So the term in the middle not only contains K0 at all.
Term in the middle not only contains.
It's like you have to.
Oh yeah. Of course. Yeah. I'm just saying that in perturbation. Yes, exactly. A2 plus. Yeah. This is just identity, right? This is just what it is.
This formula is just describing a single particle that evolves in a space-time that gives some local potential, right? If we are considering many body problem in front of you,
this is a okay. Yeah, go ahead.
So as I see here, we just describe a single particle. So how we use this?
All right. Allow me. That's the rest of the lecture. We're gonna define path integrals for quantum fields, right? And then we'll do a similar thing over there. Once I talk quantum fields, right, it's already one shot, Fox space. Well, not Fox space, but it's multi-particle, all particles at once, right? So I'm motivating this because this is 0+1 dimensional quantum mechanics, field theory. Here, everything is easier to understand. Once we go over there, I'm just going to do the path integral for fields.
So this, what does like overlap of incoming and outcoming pictures just tell us?
All right. Very good. Why do we look at S matrix? Why do we calculate S matrix? Because that's what we can observe, right? How do we observe S matrix? You're an experimental cross section. We're gonna go through the cross section, but what it is basically we bring in two beams of protons, initially really far away. We accelerate them separately, right? And they were so far away that they were not feeling any potential, right? So that's your in state. We collide them, a whole bunch of crap comes out, and once they come out, we see them in these detectors that you know a lot better than I do. They're like a couple of meters or a couple of meters away, or feet in the US, a couple of feet away, right? And you see them over there, and they're far enough that they are no longer the interaction term is irrelevant. So then you look at that's your side out, right? But cross section is about like figuring out this. Well, we're gonna discuss this. By the way, scattering is a very elegant way of thinking about physics. I just want to say that, like, let me give you an example because this might come up in your research. You could probe things using any interaction using scattering, right? For example, gravitational interaction, right? Like, there's a comet that comes, interacts with sun's gravitational wave and scatters and goes away. That's a scattering problem. That's literally a scattering problem. It was moving freely, comes and interacts with the classical scattering problem. Just goes away. It's a classical scattering problem, but it's still representation theory wise very similar. Anyway, I just said that because I was just reviewing. Oh, it's being recorded anyway. Never mind. All right. let's just say that the techniques of quantum field theory are being used to study classical scattering of objects, for example, black hole mergers. They're scattering problems. Could be formalized scattering problems. All right, good. So that's semantics. We're going to come back to this. But there are other things that you might ask about, like there might be, you want to be interested in other observables. What are the other observables? Time-ordered correlation functions in interacting vacuum. This is more nuanced and more detailed, right? We could measure correlation functions, and the correlation functions, the operators are, say, near each other, and you're doing this in the vacuum of the interacting theory, right? With this turning on and off the interaction, it's sort of like we're hiding the complexity of dealing with the interacting vacuum. But this, you have to face it. This is the interacting. I want to calculate this correlation function, right? We're going to see that this is intimately tied to the S matrix. So first, let me just say that we could calculate this using path integrals. How do you do this? Well, look at this expression. Insert S prime and S, some complete basis of states. Doesn't matter what. All right. So let me just first, you see the equations. I'm going to draw the pictures. Again, these are diagrams for to guide, right? So what it is so this is some particular time t. You have the vacuum of the interacting theory, right? And let's say you put in some operators here, some operator at this point. I'm not doing quantum. I'm not doing QFT. Some operator here, some operator here. I don't know, so a bunch of operators inverted, right? So you calculate that correlation function, or you could just have operators separated by a tiny amount of time, but you still calculate the expectation value of this operator in the interacting. That's what we're going to extract. Good. So the issue is the following. If the theory is interacting, this QITI, this is something natural for free theory, basically, for free theory, right? In an interacting theory, the vacuum will have some sort of pretty overlap with this kind of stuff. What we're going to do is we're going to play a trick that we just played, even though I didn't explain it. I'm going to put a resolution of identity here and a resolution of identity here, right? At some time 0, say. Now, what this is S prime e to the power of minus IHTIH QI, right? Similarly. Now, I'm going to take T to T times 1 minus I epsilon. This I epsilon is the same I epsilon that we needed to use to tame the Fourier transform in time. It's the same one. And then take the limit of t going to infinity. What this does is, well, let's take e to the power of minus I. Let me write it on the board. Yeah, actually, here it is. Let me write it. What is e to the power of minus IHT? This is sum over e t. Okay. So what am I doing? I'm adding this minus, this, like this. So this expression is minus e to the power of I pt e2 minus epsilon e. Oh no, sorry, t1 minus. Sorry, that's good. T. All right. Now I'm going to take t to infinity. What happens? Well, first thing you might say is that they all die, right? But what happens is that all the excited states, that the coefficient is going to be exponentially, it's going to suffer an exponential suppression. The only term the term that suffers the least suppression is the vacuum, right? So in this limit, as I take this limit, I also normalize, I can identify, pick out the contribution of vacuum. This basically projects to the vacuum. This guy in this limit projects to the vacuum. It's a projection to the vacuum. So I'm doing that, taking the limit of t going to infinity. Once you learn about Euclidean path integrals, blah, 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 this is a bread and butter. We do this all the time. Right? So what happens is the following. This limit, this term, when I take this limit, I'm going to get the QFS is going to just give me a projection down to the vacuum. So in this expression, I obtain vacuum projection here, vacuum projection here. Now it's a good. Now you notice that this is the vacuum of the interacting, right? This is the correlation function you're after, and these are the leftover terms. So you could isolate this term by taking the limit this way. Now we wrote everything in terms of a bunch of propagators. So the path integral expression for it is obvious. I played all this game so that I write everything in terms of a propagator, and then I know the path integral for a propagator. Or a bunch of operating insertions. So indeed, using path integrals, you could talk about the S matrix, we compute the S matrix, you could compute the correlation functions. There's a beautiful connection between correlation functions and the S matrix. We're going to come back to that. All right, any questions about this? So, oh God, there's still one more thing I want to say before talking about field theory. All right. Let me just jump here. Now, I'm going to say it. Let me just say the words. What happens if you do an analytic continuation this way, Wick rotation, right? This is quantum mechanics. Right? In quantum mechanics, what were we solving? We're solving the Schrodinger equation. Then the propagator was the green function for the Schrodinger equation. So what was the Schrodinger equation? Schrodinger equation was minus I h bar del t minus h side. When we talked about the Schrodinger operator, it was a prime x t delta x prime x t prime t. That might be h bars. This is the structure of it. Okay. All right. What happens if I do this change of variables? What do I get? What happens to my equation? Let me say free particle. So free particle Hamiltonian is this. What equation do I get? I get I get minus minus del t minus L squared over 2m psi is equal to 0. Similarly, I get minus del t minus del squared over 2m. This is a. What's the name of this equation? Heat equation? Heat equation. This is the heat equation. Right? The propagator, this is the propagator for the heat equation, it has a name. Heat kernel. Right? So there's a nice way to go between quantum mechanics and these path integrals and thermal physics, classical physics. This should not surprise you. At the very beginning of the course, I said there is a trick you could do. We said field theory comes up in thermal in the low energy limit of fine temperature classical physics. It also comes up in quantum mechanics, right? When you formulate it. Here you have quantum fluctuations, right? Here you have thermal fluctuations. That's what you're solving. Here you have probability distributions that diffuse. Your wave function is a probability distribution for initial configuration, it just diffuses. Here, your wave function is wave function. How does it evolve? Free particle, it just expands. Same phenomenon. Famously, heat equation has absolutely no, is non-local, right? There's a non-zero probability for the particle to just jump arbitrarily far away. And the same phenomenon that you could not do the same. So under this transformation, what happens to our propagator? So we had Q of F, T of F, e to minus IH, T F minus I don't wanna write, I'm not happy. No, I don't wanna. Sorry. UF, TF, UI, TI is this. If you do a Wick rotation, you're gonna get e to minus tau f minus tau I. There's an h bar here, right? H ui ui. Right? Does anyone know a name for this? In statistical physics. No. It's called the transition matrix. Partition, it becomes partition function if you look at the diagonal elements of this and integrate over. That becomes trace of e2 minus del tau h. It's a partition function when you put this in. Anyway, so let's skip this. I had more discussion of this. And by the way, this setting these two equal means what? It means doing a path integral on a circle. Right? Because you identify Q of F with Qi. So the way to calculate the partition function of a thermal system, classical system, is to do a path integral on a cylinder. This is the thermal cylinder. The circumference of the cylinder beta is this. This sits here. Right? There's a nice language that goes between the two. I just want to flash this. This goes with the name of classical quantum correspondence. The thing you need to keep in mind is that, first of all, heat equation goes to Schrodinger equation. Finite temperature classical system in d+1 spatial dimension is up to Wick rotation equivalent to quantum system in d spatial dimensions. We pay cost of a dimension. One of them is equilibrium physics. There's no time independence, right? The other one is dynamics. All right, that's. Are there any questions? I need 25 minutes for any questions? We might or might not have time to get there, but there's an approach to quantum field theory in the following sense. That relies on this. It says there's absolutely no problem in defining the partition function and performing path integrals. This is Euclidean space-time, right? If you look at the metric of this, this is just dx squared plus dx1 plus dx squared plus d tau squared, right? So these are the bunch of, here your correlation functions are going to be Euclidean correlation functions. They have a natural interpretation in terms of fluctuation, thermal fluctuations. So there's an attempt to, one approach to quantum field theory is to say, we're going to start with Euclidean correlators, familiar from transition matrices and statistical physics. Then we're gonna make sense of this analytic continuation using some complex analysis magic, and that defines the quantum field theory. This approach, this way of thinking about things, was very popular in the 60s and 70s, like Whiteman, those guys. So Whiteman is real time, but there's a lot of discussion of this. There's a comeback of those ideas when people realize that this way of thinking about things in the context of conformal field theory is also extremely useful. So my generation also, like, we started learning about this stuff at the same time as quantum field theory. And your generation will probably have to do that. I might include one lecture on that. This is another approach to quantum field theory. As I said, you start with a bunch of correlation functions, thermal correlation function. You try to analytically do. This looks like some crazy magic, but try to make sense of it. And then you'll have to reconstruct the Hilbert space. In this way of thinking about stuff, the input of the theory is a bunch of functions that have to satisfy a bunch of properties. Then out of that, you have to build a Hilbert space and observables and all of that. All right. Any questions? So in the remaining 25 minutes, we're gonna switch gears and talk about path integrals for scalar fields. We're gonna do this for free field theory for now. Then we're gonna talk about interactions. But today it's going to be path integrals for field theory. What's gonna happen is, by now hopefully clear, your Q hat and P hat are gonna become phi A and pi A. In quantum mechanics, position is an observable, time is not. Quantum mechanics treats space and time differently, asymmetrically. In quantum field theory, we need relativity. We need to treat space and time symmetrically. We do that not by promoting Q to be an operator, by making X also a parameter. So in quantum field theory, both position and time are just parameters. The fields are the quantum objects. All right? So what changes in the path integral? We still talking about propagator, right? Now, the propagator is this. Is going to be the propagator is going to be like this. At some time ti, this is sometime tf, you have a field configuration phi of x of ti, and have another field configuration here. I'm going to call this phi minus, phi plus of x and tf. The propagator is the overlap between these two. And your path integral is precisely the same. You will have to path integrate not over all paths that go from here to here, but all the functions that interpolate from this piece. Right? You integrate over all functions that have this boundary value and this boundary value. Of course, I'm not going to repeat those steps. Am I going to repeat those steps? I'm not going to repeat those steps. Of course, as before, when you try to massage this expression to a path integral, step by step, you could go through it, and I'm trying. Hopefully, I'll remember to include it as a homework problem. But we step by step, we just go through the process that we did, the steps that we did to manipulate this into path integral. Well, first, let me just firstly, what you do, you notice that this is 5 plus of x, this is 5 minus of x, and then there's e to the power of minus ih tf minus ti. Now this Hamiltonian is a function of phi a and pi a, right? So you have to insert resolution of identities will be a set of kets of phi a's and pi a's, right? You're going to end up with a path integral in the phase space, which is phi a and pi a's. Right? That's the phase space. Because the Hamiltonian of free fields is second order in pi a, right? You could perform that explicitly. You're left with a path integral only on phi a's, hence the expression I told you. And the path integral over all functions with this boundary value and this boundary. All right, is that philosophy clear? So we're gonna do the calculation. The action up to a total derivative is this. I've already done the I epsilon here. What I epsilon is that? It's Feynman. When you write down the action this way, is it clear that this is a free action? I've just done integration by parts, right? You immediately see that the propagator is the inverse of this, right? The propagator is the inverse of the kernel up there. You knew that's going to be the case. So this is Feynman. This is Feynman epsilon. Good. So this is the action you're working with. Good. You have a generating, you define a generating function. What is a generating functional? Well, sorry, let me just first say this. Let's, for the moment, path integrate, take ti, remove ti and ti. We're just going to path integrate over the whole space. Right? Let's just ignore that for a second. We're going to introduce a source, integral of dx jx phi x. I'll try to explain the physics of this source in a bit. All right, I can do that. This is the same source that we introduced. It's familiar from thermodynamics, hopefully. Right? It's just what generating functionals are. For now, this is just an object I can define. All integrals here are space-time integrals, all right? I'm gonna pick free action, the action of free field theory, this one, in here. And I already put the Feynman prescription here in anticipation that it's gonna simplify my life. This is the path integral I have to do for the free fields. This is the generating functional of the free fields. The next few steps are crucial, very crucial, very important, that at least it has to click. All right, everybody's with me? Can you tell what the point of this expression is? Why do we define generating functionals? If you take functional derivatives with respect to a bunch of j's, sorry. So first of all, this integral is everywhere in space, even though I've written it like this. This is jx phi x integrated over all points in x. So if I take so z0 of j is a function, right? If I take derivative with respect to j of x1, what happens? It brings down phi of x1. I'm calculating a 1-point function. If I have to set j equals 0 at the end, right? I'm going to take a bunch of derivatives and set j to 0 at the very end. And that gives me a bunch of correlation functions. That's why it's called a generating function. It's a trick. All right, so let's calculate this, and then we're going to do that. So of course you would not be surprised that the Feynman propagator is the green function for this. Right now I'm using the relativistic notation, and all you need to do is you make the following shift of variables. So you send phi of x to phi prime of x, integral of the Feynman propagator jy. Phi of x is a dummy function, right? I'm integrating over it. So field redefinitions are my frames, right? I'm integrating over them. So I can do that. Under such a change, I'm going to end up with e to the power of I s naught of phi prime, the path integral over phi prime, and then a contribution that does not depend on phi. So this comes out completely. And my z naught of j is z naught of 0 multiplied by this expression. Just completing a square. You recall what the Feynman propagator was. This was the expression for it covariantly. What is z naught of 0? At some deep level, it doesn't matter what it is, but it's a homework problem you could do, and you find that it is the determinant of this operator to power minus half. It's just an infinite set of Gaussian integrals. That's all it is. Let me pause here. There's a lot that I'm presenting. Are there any questions about this? So I defined a generating functional. And after I use the fact that phi is a dummy variable I'm integrating over to change my, to shift my field phi. I performed the integral and I wrote z0 of j. 0 here means free. Free partition function, generating functional, free generating functional, in terms of free generating functional with no source. Right? And free generating function, and what came out is that e to minus half. There's a double integral of jx Feynman propagator jy. That's non-local, right? Are there any questions? Let's see how to do my time. Yeah.
What happens to the bound when you make this change?
These boundaries, I'm intentionally avoiding them. I'm going to take them to minus infinity for reasons. You really want to avoid. Can you tell how things change when you include boundaries?
You're just going to acquire that term in your boundaries, right? So.
Well, for one thing, when I wrote this, I took the standard expression of del mu phi squared, and I did integration by parts. You'll pick up boundary terms there. There will be boundary terms all over the place. But let's avoid that, because I would say that that's a question that I know how to answer that question, but it's technically very involved. And it won't be important for us, because all we need to work out, what we need is a generating functional for all space-time. We're going to take I to minus infinity, tf to plus infinity. Remember that at the end of the day, we're going to calculate S matrices. And then I gave you a trick to calculate correlation functions coming from S matrices. That's a very good question, though. If you did the calculation literally with those in mind, well, the calculation is something that is done in like Feynman Hooks. It's somewhat confusing. You're gonna confuse yourself easily, but it's a very good calculation. All right, good. So what we're gonna do is we're gonna take z naught of j divided by z naught of 0, and the result is basically this, right? Z naught of j divided by z naught of 0 is just this expression. What is the interpretation of that? Let me write it here. Yeah, this is what the expression is, right? I can interpret this expression as the expectation value of time ordered e to the power of I j phi in the interacting back. Because e to the power, this I can write as e to the power of I s naught of phi, e to the power of I integral of j phi. And I told you that every time you have an operator, you're doing a path integral with that operator, that what you're calculating is the time ordered, the expectation value of time ordered for it. Sorry, I said interacting. I said the word interacting. That was nonsense. We're talking free period. Free vacuum. All right. So this is what this object is. Very good. So what we want to calculate, let's first calculate the k-point correlation functions. These are the time ordered operating insertions like this. These are space-time, right? All that this is just you take derivatives of z0j, generating function of j with respect to these guys, divide by z0 and send j to 0. Wait, did I say this right? Yeah, I think I said this right. No, I'm not happy with this. This should be 0. I believe this should be z0, 0. Yeah. Because what does this calculate for you? This will calculate for you. Yeah, so I need to divide by this guy. I need to divide by this guy. This will bring down a bunch of phi's, time ordered, and you need to. Yes, that is correct. This is z0. Well, actually, no, it's silly because I put j equals 0 here. So yeah, they're the same thing. All right, good. So very good. Oh, I now I remember why I did it this way, because this way I can view it as the nth derivative of log of zzj, z naught j. Right? Okay, so let's calculate log of z naught j. This is what log of z naught j is. When I take derivatives, z0, this is a shift. It doesn't come out. Right? So let's take our correlation functions, phi of x1 to phi of xn are del jx1, oh, sorry, del jxn log of z naught j equals 0, right? Let's take derivatives. Let me pause here. Is that good? All right, let's take derivatives. What do you get when you take one derivative with respect to j? Well, the expression is second. The expression is second order in j. If you take one derivative with respect to j, you end up with delta f j. J survives. When you set j equals 0, it gets 0. Can you instantly generalize? If you have n operating insertions, you're, well, we'll get there. Okay, so that's the 1-point function. 1-point function of the field is 0. Was that expected? Is that surprising? It's expected. Why is it expected? How did you know that the 1 function of scalar field has to be 0? Z2, phi going to minus phi is a symmetry, right? So whatever the expectation value of this is, it has to be the same as the expectation value of minus phi, therefore it has to be 0. All right, let's take two derivatives. Time order, you see this is the magic of path integrals. What comes out is just naturally time ordered, and that's what we want, right? You take two derivatives, you get I, the propagator, right? Minus this, there are extra terms, but these vanish when you set j equals 0. Is it clear why I have these terms? Go through it. Go through it. Maybe I'm doing this too fast, but you should definitely repeat these calculations. They're extra terms. So in free field theory, what happens is this: as you take, like when you calculate an odd correlation function of odd number of operators, you have to take an odd number of derivatives, and there will always be a J survivor. When you set J equals 0, that vanishes all the odd point functions at 0 in free scalar field. Good. All right. Before talking about how the even point function look like, let's just do 4-point function. But let's look at this. I'm going to invent a diagrammatic structure for you. J delta Fj. This J is the source. Can you see the physics of this? What the J does for me is it creates a particle. Then delta F is propagator, and then the second J kills the particle. Right? This is free field theory. I have particle number conservation. The theory will not spontaneously create particles, right? So I had to introduce a source to kick one out of the vacuum, evolve it, and just kill it, right? So this is that diagram, but these are diagrams, right? These are integrals, as usual. These are Feynman diagrams. So z0 of j divided by z0, 0 is e to the power of minus half this diagram. So that is 1 minus half this diagram plus 8 this diagram squared plus so on and so forth. All right? This is where the diagrams become magical. You want to calculate the 4-point function? Take derivatives. What you find is that you're going to end up, well, there are 4 points that are inserted, right? You're going to end up with this term, which is, you create particle 1 and 2, there's a propagator between them. 3 and 4, there's a propagator between them. There's you find this term. You find this term. There are 3 terms that you find. As a matter of fact, so this is the structure of the, just take derivatives and see, right? As a matter of fact, this structure survives at higher orders and it's called Wick's theorem, right? So it's a rule for reducing time order correlators and writing them in terms of just like the property, right? So for example, how does the 8-point function look like? So you put 8 of these J's, right? And you should sum over all pairs, right? Propagating between all of them. All right, but I'm gonna describe Wick's theorem in a little bit of a more general context. So this calculation will calculate this method will calculate all the correlation functions for you, right? What I'm gonna do next is the following. Take the time ordered operator, subtract from it is vacuum expectation value, right? This is what you obtain. It's the time, it's the normal ordered correlator. Why? What is the expectation value of the normal order correlated in the vacuum? What's the definition of normal order correlator? So if you have a normal order correlator, exactly. So normal order correlator of phi x1 all the way to phi xn. Each of these guys will have an A and A dagger term. Right? So you're gonna end up with a whole bunch of A dagger, different positions, right? Normal ordering says that move all the A's to the left. So what's the expectation value of that in the vacuum? 0. Because you always have at least one. So the normal order correlator it's the correlator with this 1-point function removed. Right? At least for the 2-point function, you could see that explicitly. Sorry, I said this only for 2-point function. More generally, take this operator, and the normal ordered thing is just its expectation value removed, and this is what its expectation value is. This gives you an algorithmic way to just calculate your favorite correlation function really, really fast in the language of these diagrams. So, for example, you want to write down the time order 4-point function. This is the normal order 4-point function plus the normal order, these two with the 2-point function plus all the permutations plus these expectation values. You could prove this relation starting from this. You see the rest of how it works, right? So there's a very nice Wick's theorem constructs a very, very nice relation between normal order operators and time orders, right? All right, I think this is where I want to stop, and over time I don't have time to talk about mass gap. All right. Any questions? What did we discuss? We discussed whatever we discussed before scalar field. I'm just going to review very quickly scalar field theory. We looked at the path integral, or at least I argued based on the quantum mechanics case, the path integral for a free field, scalar free field. It's a path integral over all phase space configuration of the field, because in free field theory, the kinetic part of the Hamiltonian free fields is just pi squared. You could do that explicitly, and you end up with real space path integral for the fields. So you're path integrating over all field configurations in the field. Good. All right. Then we said we wanted to talk about how you could. No, then we just evaluated the generating functional. It had a very nice form. It was just J propagator J, Feynman propagator, right? Exponential. E to minus half J propagator J. These parameters are going to keep track of it. You take derivatives and it gives you X. Set J equals 0, it gives you all the time order correlations. Any questions? Not. Thanks so much.